So as I said a moment ago, but I'm recording now, so I'll say it again. Up to this point, we talked about what light is. It's an electromagnetic wave caused by wiggling charges. We then looked at the different types of light that exist in the electromagnetic spectrum, starting from low energy radio waves all the way up to the highest energy gamma rays. And then yesterday we talked about sources of light, things that are luminous, and I tried to stress to you that from here on in, when we talk about light, when I say light, I'm implying visible light, light that we can see. So yesterday was about sources of visible light, all right? All those other parts of the electromagnetic radiation spectrum we talked about when we talked about the sources, right? I think for gamma, I said it was nuclear reactions produce gamma radiation. But we can't see that, so we're not worried about that. So what do we want to talk about today? We want to talk about how light travels. This is called the ray model of light, and this is simply a model that we use that allows us to study and look at the way light behaves when it runs into things. So we want to talk now about what happens when light encounters stuff, all right? And in the end, I'm going to write it down, but there's really only three things that can happen when light encounters things. It can either bounce off of it, it can go through it as if it's transparent, or it can be absorbed by it. Those are the three only possibilities that light can do when it runs into something. But we want a way in order to draw pictures of these things, and the method we use to draw pictures of light and how it behaves is called the ray model of light. All right, we call it a light ray. Okay, so how does light travel? Well, really fast and in straight lines, all right? It travels so fast, am I going to give the number? Sure, I'll give you the number. The speed, actually, it's such a special number. Exciting. Hello.
Can I bug you one
Yep.
second? I can get the volume to work.
Okay, hold on one second. I'm going to pause this for a second. Okay, so I was going to write down the speed, but I forgot I had it on the next slide. So there it is right there. I don't even have my microphone. It's a funny sounding video. That's okay. The speed of light. So it travels fast and it travels in straight lines. We're going to cover these two kind of ideas in two separate little pieces here. And these are approximate numbers. The speed of light is actually something like 2.998 something, you know. It's a very you know, we know it more accurately than just one significant digit here. But another way to write this, we can also write this as being 3 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8 meters per second, all right? That's really fast. The speed of sound, and the only reason I'm talking about the speed of sound is because in order to have an appreciation to how fast light is, it's kind of useful to think about how fast sound goes. And again, it's approximately 300 meters per second. The speed of sound is very temperature dependent. The warmer the air is, the faster sound will travel, all right? It's actually about 330, and that's at like room temperature, so it's about 330 meters per second at room temperature. But just for the sake of some calculations that we're going to do in a moment, just to compare these two things, we're going to just put it at 300, so it's a nice, easy number to work with, okay? So you may have noticed that if you're, say, at a baseball game, like even I was going to say a professional ball game, but it doesn't have to be, or even at a soccer field and soccer going on over there or something like that, and they're way far away and somebody does something, you can see them, they either hit the ball or they hit the post or something. There's a great delay in hearing the sound from that particular thing. Have you ever noticed that before? Yeah, yes, good, excellent, that's good. And that's because there's a vast difference in the speed of light than the speed of sound. As light bounces off them and enters your eye, it's practically instantaneous. The light travels so much faster than the sound that when it happens, you see it. But it takes an elongated period of time for the sound to get to your ear, and therefore you hear the delay, all right? The classic example of this is lightning, right? You've all encountered that before. You see the lightning flash, and moments later you hear the thunder, and that's because, again, when the lightning strikes, it's pretty well instantaneous. The light gets to your eyes very quickly. Yes? What am I doing here? When we hear an event, we see the light almost instantaneously. The sound then catches up, and we hear, yes, there's a mistake in there. Excellent. Yeah, I'll have to fix that. Because we hear with our ear. Yeah, see, I forgot about that one. All right. And we hear the event later. Good fix. Let's write down a couple examples of that. Number one, let's write down lightning. And I'm going to do a couple of calculations underneath both of these. So leave a couple of lines there, or leave a little bit of space. Finished writing already? Awesome. Everyone needs to pick it up a little bit here. You'll have to see exercise science teachers for that, not me. After we see the lightning strike, it takes time to hear. Look, I got the right here there. Hear the thunder. And number two example that indicates the speed of light, it takes the sun's light 8.5 minutes to reach the Earth. So even though light is incredibly fast for us here on Earth, we see an event, it's pretty well happening exactly at that time. Not exactly, but pretty close. Even though that's the case, when you get to astronomical distances, it takes time for the light to travel through space. In terms of the lightning and the thunder, we're all told as children, maybe by our parents because, well, they may not, it might be an old wives' tale, but what do you do when you see the lightning? What are you supposed to do? And they say, when you're still like scared, you see the lightning, and what are you supposed to do? You count, and you count in seconds, right? So you don't want to count too fast. And what does it mean? What are you told about that? Let's say you count 3 seconds. Ooh. 3 kilometers away, right? I remember when I was a kid, 3 miles away, 3 kilometers away. Let's do a quick little calculation to see how correct that is. Let's say that you see the lightning and the time it takes is 3 seconds, all right? And this is the sound getting to us. So the speed of the sound, what was the speed of sound? 300, about 300. About 300, what was the unit? Meters per second, right? M/S, meters per second. So if I want to find the distance, if I have 300 meters per second, and it's been traveling for 3 seconds, what do I have to do mathematically to those numbers? It's traveling 300 meters per individual second, and it's been traveling for 3 seconds. Yep, you multiply them. 300 meters per second times 3 seconds, and these seconds cancel away, and you'll notice you'll be left with a unit of meters, and I'm kind of running out of room here, so I'll put it down here. And what do you get for an answer? Yep. 900 meters. 900 meters. Approximately 1 kilometer. You've been lied to. It's a lot closer. It's a lot closer. Oh, look, Sammy's worried now. What the? You mean every time I counted to 6, it was not 6 kilometers away, it was only 2 kilometers away? Now she's freaking out for all those storms in the past. That's exciting. Wilson, what are you going to add to the conversation?
It'd be cold and it's probably raining.
Yep.
Things sound probably differently.
That's right. It's about 330 at, like, say, room temperature, right? So does the rain make it colder? Actually, normally thunderstorms happen during hot, humid days, so it actually might be a faster speed of light. Again, I'm just putting approximate numbers there. There's also all kinds of other effects. If the wind is blowing, it literally carries the sound with it. So if the wind is blowing at you, the sound will be coming towards you with the wind. But if the wind is moving away from you, the sound is actually being taken away with the wind. So this is a very simplistic calculation, but from the speeds, it would be 1 kilometer. Would it always be 1 kilometer? Not necessarily. Wind and temperature and all kinds of things have an effect in a practical sense, all right? But just by looking at the speeds, if the air was calm, it would actually only be 1 kilometer away. A little freaky, eh? Isn't that fun? So next time you guys can get really worried about that. All right, that's fine. It takes the sun's light 8.5 minutes to reach the Earth. We could actually then measure the sun-Earth distance the same way. In this case, the time is 8.5 minutes. The V is, we'll use the scientific notation on this one, 3 times 10 to the 8th meters per second. All right, because this is light this time. We're not looking at the sound. And again, I want the D. So again, I'm going to have to multiply, but I've got a problem with my calculation at this point in time. I can't multiply my minutes. What's so funny? Really, what's so funny? What? Nothing's funny? Okay. Then let's continue. So I can't multiply my minutes by my meters per second, so I need to convert that into seconds. Could somebody convert 8.5 minutes into seconds, please? Yep. Did you calculate it out for me? 100, or did you guess? 110? Beautiful. 510? 510 meters. Sorry, seconds. Seconds. All right. So let's now do the calculation for the distance from the Earth to the Sun. 3 times 10 to the 8th multiplied by 510. And I'll take a number for that when someone calculates it for me. You got a number? It'd be 1530. Yep, 1530 times 10 to the power of 8. So I'd want to change it back to scientific notation. So that means I've got to move it back over. Yeah, what do you got? Times 10 to the power of 11 meters, which is the same as what that is, right? We just moved the decimal over to turn into scientific notation. That's a pretty big number. It's a pretty big number of meters. Again, that's only to the sun from the Earth. In actual fact, we use the speed of light to measure very large astronomical distances. If we're talking about distance to stars, the meters are so great that it really has no meaning to put it in meters. We would have such a big power of 10 that the number is so large. Does anybody know what unit that astronomers use to measure distances to stars? Yep, Mackenzie? Light years. A light year. 1 light year. All right? 1 light year is the distance light would travel in a year. We could calculate it. It would be 365 days times 24 hours times 60 minutes times 60 seconds to get to seconds times 3 times 10 to the 8th, the speed, and you're going to get a really big number. But what that means is, if a star, the closest star to our sun, is about 4 light years away, It's in the Andromeda galaxy. Anyway, sorry, it's not in the Andromeda galaxy. It's in our galaxy, but it's very close. It's towards the sky that has the Andromeda galaxy in it. It doesn't matter. Anyway, and if you look at that star, the light that you're seeing at night is 4 years old. That light was created by that star 4 years ago, and it's been traveling at the speed of light since then, and it enters your eye, and you catch that little bit of light in the back of your eye, and you see it. You see the star. And then that light's path comes to an end. You've absorbed it in your eye, and you see the star. So we can use the speed of light to designate very long distances. Okay. Rectilinear propagation. Rectilinear, what a great word. It means straight line travel. Light travels in straight lines until it encounters something. If it encounters something, it can be deflected, reflected, which is the same thing, it can be kind of deflected on its way, or it can be absorbed, or when it goes through something transparent, it can actually be bent a little bit by the transparent substance, like glass. How do we know that light travels in straight lines? We see shadows. Shadows are an example of rectilinear propagation. This is a candle. It's this very small candle. You don't have to, for your notes, because I'm going to ask you to draw pictures. For your notes, just draw a tiny little flame there, right? Right? Draw a flame just like this. Put a little thing on the inside there, and then you can put the candle, right? So this first one we're going to deal with is a small point of light. So I put a tiny little candle there to represent that we're dealing with a tiny point of light, all right? I'm not dealing with a big, wide point of light. And I put an object out in front of it. And you can imagine we're looking top down and the light is shining. And there are rays coming from this light source in all directions, just like when you were a kid and you drew the sun's rays, all right? Now, there are an infinite number of rays coming from a light source. Every point in space you can imagine having rays coming out from it. That would be a very difficult thing to draw. It would be like shading the whole thing with light. And that's what happens when a real light source is presenting its light. This whole thing, we imagine, has lots of rays spreading from it, and all of those rays cover us and we're covered with light. But when we draw optical pictures, and that's what we're getting into, we're going to be drawing what happens when light encounters mirrors. We're going to be drawing what happens when light encounters lenses. When we draw optical pictures, 2 rays is all we need to find the important optical thing that we're looking for. In this case, the 2 rays that we're concerned about are the one that grazes the object on either side. But it's always 2 rays. You always need 2 rays to find the thing that you're looking for. So I draw a ray, and I'm going to try to make it straight. And you know what? If you have your rulers here, this is great, because we're going to be drawing all kinds of diagrams. And when we draw ray diagrams, we should always be using rulers. And I had some rulers here, and now I don't know where the rulers went. I put them on the cart there. No, if you've got a ruler, get it out. If you don't have a ruler, I had rulers here, and now I've misplaced my rulers. I had really good rulers. I put them away in such a good spot. There they are. So here I've got a bunch of good metal rulers. If you need a ruler, come on up and grab them. Or you could just use the edge of your calculator case. Or perhaps there's a ruler right there. You could just go and grab one. Oh, okay. All right. Now, I can't use a ruler on the smartboard because the smartboard can only be contacted in one position in order for it to understand where it is. So I'm cheating. I'm not using a ruler. But the one ray we want has to cut across there and touch that. Yeah, I'll call that a success. That's not bad. and the other ray is going to come across here, and I got to kind of get it to aim over there and touch that. Yeah, we'll say that's pretty good. All right? And over here we have light, but we're not going to color it in and shave it. And over here we have dark. All right? And this dark part of the shadow is called the umbra. It's the darkest part of the shadow. And when you have a tiny little source of light, you get what we call a sharp shadow. You get a defined point between the light and the dark. And my projector right there is actually a pretty small port of light. I shouldn't have looked in the projector. It's really bright. Okay, it's actually a really small point of light in there. So if I put my hand in front of it, you can see a nice sharp shadow. Right? See the sharp shadow? We'll turn this light off. Ta-da, nice sharp shadow. You can do those things. No, I don't know how to do that stuff. We see the sharp shadow? And that's because rays are coming past my hands, and there's the dark part, the umbra, and then there's the light part. We okay with that? Okay? Now, if the object is big, we get, you can define a light ray. It displays the straight line path of the light. As I said, there's infinite numbers of light rays you could draw, but there's only two light rays that are going to define the things we're looking for. It's going to be true all the way through the unit. Whether we're working with mirrors or lenses or shadows, it seems that two rays are important to locate something, whether it's a shadow or an image. So next I want to talk about what happens. Oh, yeah, no, you can write that down. I keep forgetting that there's animations on this. Sharp shadows are observed if the source is small and the object is large compared to the source. Now notice I said large compared to the source. Again, my hand way back here, that source is way over there. It's so small. My hand, pretty big. Now, if I have a large light source, then I get a different pattern of shadows. So this is my large source. Again, for you, if you're drawing it, just draw it as a big candle. There you go, the middle of the candle, that type of thing. That's good enough. And I'm worried about the top of the candle and the bottom of the candle because the whole candle is giving off rays. It's giving off all kinds of rays. But again, I'm only interested in two rays. And I'm only interested in the extremes of the candle. Yeah, there's rays given off by all of the candle, but the extremes are the important part. So I want to take into consideration the shadow created by the top of the flame. So I'm going to put my two lines there. The top of the flame, that creates a shadow. All right? Oh, I should have added, and I'll add it now. Rays must have arrows on them because they represent the direction of the light ray. And I'm also going to create two rays created by the bottom of the candle. And those rays are cutting across there. So I got two sets of rays, one coming from the top, one coming from the bottom. And you'll notice we have overlapping shadows. The shadow from the top is actually being illuminated by the bottom part of the candle. And the shadow from the bottom is being illuminated from the top part of the candle. It means we have three distinct regions for something that's large. Over here, it's light. Same with down here. It's bright light. down in here, right behind the object, it's very dark. Again, it's the darkest of dark. It's called the umbra again. Umbra. And then in these two regions here, yep, question? Yeah, yes, I'm going to talk about eclipses right now in a moment. So if you've talked about solar and lunar eclipses, we're going to see it again, except now we're thinking of it in terms of how the light is behaving, but you probably were taught that as well. Same terms, correct. So if you've learned this, what was the in-between one? Anybody remember? Yeah, Jillian? Penumbra. Penumbra. I do not know the origins of those words. Penumbra is like it's not as dark as the dark and it's not as light as the light, right? It's an in-between shadow. Why? Because it's a shadow from one source and not the shadow from the other source. So this is penumbra. Okay? Okay? I can use my lamp to simulate a large source as well, because large is all relative. If I have my hand way back here, then that little lamp way back there, even in my eyes, it looks so tiny and small. But if I were to have my face right in front of the lamp, it'd look like a pretty big lamp. Right? I like to think of it in terms of what a deer would see if it was standing out on the road. Right? Imagine a deer standing out on the road and a car is coming and it's way down there and the deer goes, huh, there's something way down there. Looks like a tiny little point of light. This can't be dangerous. Deer looks away, maybe talks to his buddies in the ditch, looks back, and now the car is right there, right before it runs into the deer. That's where I'm going with this, obviously. And the headlamp is right there in front of the deer's face. What do you think the deer would think about the size of that lamp source at this point? It's pretty big. So a lamp, or even the sun to us actually behaves almost as a point, little tiny source. Because when you stand out in the summertime and you look at your shadow, do you have a sharp shadow? Yeah, your shadow's pretty sharp. You can see the edges of it. So the sun is actually behaving as if it's a tiny little thing. But the sun is huge. The reason it's behaving as a tiny little thing, why is it? It's far away. So I can still use my projector as a source to describe the light, the big object. Where do I have to put my hand? Close to it. Watch what happens to my shadow as I bring it close. Look at what happened there. Look at the edges of my shadow now. They're not as sharp anymore, are they? Right? If I bring it back to this point, you'd say, oh yeah, there we go. That's a sharp shadow. So my hand is large compared to the lamp source. But as I bring my hand in, oh, it's not sharp anymore, and it's really not sharp. And even right in there, there's hardly any real umbra. There is a little bit there. There's my finger there. Isn't that fun? So you can see it loses its sharpness because the source is so much. This could have been the same candle, and I just moved the object really close to it. Okay? All right. So fuzzy shadows. If the source is large and the object is small, again, small compared to the source. And as examples, and Megan took all the fun away from it, eclipse. The two versions of the eclipse. So, sun is the yellow one. The gray one is the moon, and the blue one is the earth. And this is going to be tough for me on the smart board because I can't use a ruler. But if you make them about those sizes, and again, in this case, the sun is fairly big compared to the moon we're going to need rays coming from the top, rays coming from the bottom. If your rays happen to graze right on past the Earth, it's okay. Don't worry about it. If they encounter the Earth, it can stop. You guys can just go Earth, Moon, Sun, if you're just labeling. And I'm going to give it a shot, but that's really far away. I don't know if I can hit that moon with that, with just a free drawing here. Ooh, I did a little cheat move. Oh well. It's not bad, but it's not great. Okay. Yeah, it does a little goofy curving thing. That's not rectilinear propagation, by the way, if you're watching my movie, because I didn't use a ruler. But you get the idea. So, down in this area right here, that is our umbra, and it is dark. If you're standing under if you're standing on the Earth in that little space, you're seeing a complete eclipse. That's a full solar eclipse. All right? Over here on the sides, we have the penumbra. And there you're seeing a partial solar eclipse. All right? You're seeing just a piece of it. Some of that light is sneaking by. I think there's a partial solar eclipse supposed to be tomorrow sometime, and I didn't get the location. I think it's in North America. We had a lunar eclipse about 2 or 3 weeks ago, right? We had one 2 or 3 weeks ago. Well, let me draw the picture for the lunar eclipse, and we'll talk about it. But we had a lunar eclipse 2 or 3 weeks ago. It was right when the moon was going down. It was awesome. It was right in the morning on the way to school. If you were up that early, was when I was on the way to school, about 7 o'clock. 6 to 7. Yep, 6 to 7. Yep. And then the moon set, and then it was done. Anyway, let's do the last example here, and let's do the lunar eclipse. So the lunar eclipse takes place at night, and it's when the Earth parks itself right between the sun and the moon. And again, I'm going to draw 2 rays from the top and 2 rays from the bottom. Oh, that was terrible. And now I'm using pink. I don't know why. That one was better. Yeah, not bad. Yeah, not bad. Again, umbra, dark, penumbra. And there's actually a color that goes along with it with a lunar eclipse. When it's in the penumbra, the light is just grazing the atmosphere of the Earth. And just like when you look at the sun setting, the sun changes to this particular color because the light has to cut across the... Yep.
Can you send your attendance to the office, please?
Yep.
Thank you.
What color does that lunar eclipse look when it's just kind of going into eclipse? Has anybody noticed that before? Or you seen it the other day? It actually makes it look red. It makes it look red. So as the moon is swinging around the sun during the eclipse, it goes into that red area, and then it starts to disappear, and there it becomes very, very dark. Yeah. And the other day when the sun was coming up and the moon was just setting, and it was right on opposite sides because the sun was coming up behind us, and the moon was setting and it was actually in that direction, right, then it actually disappeared almost into the blueness of the sky as the sun was coming up. It was really cool. If you missed it, you missed it. But if you've seen it, it was neat. Yep, it was a good one. Okay, so those are examples of rectilinear propagation. Again, kind of in my haste, in my discussion, I forgot, but every one of these rays should have arrows on them, all right? When you draw a ray, you should put an arrow on it. And it's going to become more important as we draw rays for reflection and for lenses. So, now we're ready to kind of take an official list of what happens when light strikes an object, and that's going to kind of define the things that we're going to do for the rest of this unit. So we talked about what light is, we talked about sources of light, we've now talked about the fact that light travels really fast and it travels in straight lines. And we're going to use this straight line part of the travel to explain what we see when light strikes things. So what happens to light when it strikes an object? I've already told you this, so I'm just going to bring it up. Oh, no, we'll bring that all up. Oh, and I've locked people out. So when light encounters object, number one, it can be reflected. That's the first thing that we're going to look at. Number two, it can be absorbed. And number three, it can be transmitted. All three of these kind of interactions can impart color to things. And in the grade 10 applied course, we actually take a few days and talk about color theory. I'm hoping that we've got time that I can get ahead of the other classes because I really like talking about color theory. It's really a useful idea. So we'll see whether I can get in some color theory for you guys because it really is an important thing. All of the colors we see get imparted by one of these three things. Reflected, right now, the color of your clothes are the color they are because of the way they absorb versus reflect. Some of your clothes are absorbing some colors and reflecting other colors, all right? When you look through a piece of colored glass, like a stained glass window, again, as the light comes through, some light is allowed to pass through and other colors are absorbed by the glass. So again, a combination of transmission and absorption is what results in colored transparent materials like solutions or colored glass or colored plastic, right, that you might get off of a candy wrapper or something, right, that might have a little color to it. It's a combination of absorbing certain colors. Now, we're not worried about colors for the first part of this unit. We're just worried about the rays and what direction they travel. They could be whatever color, okay? Just to define what happens in terms of transmission, something is transparent when light easily goes through it and the image can be seen clearly. An example is glass, all right? And I'm not talking about frosted glass or anything like that. I'm just talking about regular glass. We could talk about, plastic wrap, right? Anything that you can see things clearly through it. And we've already discussed these in terms of our three adjectives for chemistry. It can be translucent. Some of the light goes through and you cannot see a clear image. Again, the reason a substance might be translucent has everything to do with reflection, absorption, transmission. Some of the light might be reflected. Some of the light might be absorbed. And a very little bit of light might be transmitted. So all three things can happen at the same time. An example of translucent, right? Piece of paper, right? If I hold the paper up like this, I put my hand behind it. See, hello, you can see my hand there, right? You can't see exactly what the, the fine details of my hand are, but you can see some of the image That makes it translucent. And that's because some of the light was reflected, some of the light was absorbed, and a little bit of the light was let through. And I'm going to just put paper. You can put all kinds of different things. Frosted glass is translucent, right? Where, you can kind of see the image through it a little bit, but you can't see what it is or who it is. Opaque, no light can go through and no image can be seen. You can pick whatever you want. Like a wall is opaque. Certain solid material is opaque. The desktop is opaque. A book is opaque. With a wall. We get the idea. All right? And again, the reason I go through those terms here is because they are optical terms. They're terms that describe the way light behaves. Okay? And we're not going to write anything down for this last one. Another teacher added this slide, and I don't need that. So here we were going to draw out what happens with transparent. They can all go through translucent. Some of it doesn't, et cetera, et cetera. We're not cared about that. So that's the end of that particular first note on what is light. And I'm going to continue on and talk about reflection here in a moment. All right? So I'm going to stop this. Oh, I want to stop my recording here.